So we will start this simplified synchronous machine model. As you know, the synchronous machine, if you neglect all the dynamics, then you can represent the machine by constant source behind reactance. But this is, of course, this is the simplified model. During this course, we will develop nonlinear models of the synchronous machine. The first course, the first let me just start again. After having this simplified model, which is the constant voltage source behind reactance, you can develop a third order model if you consider the dynamics of the excitation field. You can, even the excitation field can be represented by a third order model or fourth order model, and synchronous machine third order model or fourth order model. The governor also and the mechanical control loop can be modeled by fourth order model or fifth order model. So with the synchronous machine plus the excitation loop plus the mechanical power loop, you can end up with a model of 15 or 16 order. So you can have 16 differential equations that describe the complete system. What we will do, we will start with the simplified model of synchronous machine, and later we will develop the other models for the machine, exciter, and the governor. So we will see the simplified model, and we will develop stability criteria based on this model, and with different configuration of the system. We could have single machine infinite bus system, which is the simplest system that you can have. You can have two machine system, and you can have multi-machine system. What are the stability criteria if we have any one of those systems? So this is what we will develop this class, inshallah. So simplified model, as we mentioned, then we have constant voltage behind reactance. So what you have here is the internal voltage, which is E prime with angle delta, which is a rotor angle or power angle, and this is the terminal voltage. You can take the terminal voltage here as your reference. And this is the direct X transient reactance, XD prime. And this is the current. Or you can say it's synchronous impedance at the time being. But when we say synchronous, we mean steady state. When we have transient, this is the transient reactance. But the reactance is changing from, if we have any disturbance, in the synchronous machine, so assume this is the current I of t. Assume that you have somehow you have a disturbance a three-phase fault or whatever, then the current could go very high, very short time, and then comes okay. So let us have this. This is instantaneous values. You have here a sinusoidal waveform. This is called the subtransient current. And this is few cycles or half cycles after the disturbance. With few cycles here, 10 cycles or so, this current called transient current. And after this, we call it steady state current. And if you have a disturbance, you can divide the period after the disturbance to 3 sub-periods. This is subtransient period, and this is the transient period, and this is the steady state period. The machine here is represented by the subtransient impedance. You have XD double prime, you have XQ double prime, you have E double prime, you have ED double prime. So double prime means subtransient period. We are talking about subtransient period. 1 prime means transient period. Then you have XD prime, you have EQ prime, you have ED prime. So this is the transient period. And this is the steady state. You have X synchronous, E, Q, or whatever, or ED, if you have ED. So the prime here refers to transient period. At steady state, it will be X synchronous or XD double prime for subtransient period. The phasor diagram of this simple circuit is that you have a reference. The reference could be VT or could be some other phasor. Usually when we have here a generator and you have a transformer and then you have a transmission line and this is the infinite bus. Usually we take the infinite bus voltage as our reference. Usually we take, and this is the system, huge system, so this is our reference here. In this case, VT, terminal voltage, will have an angle, let us say gamma, and this EQ prime have an angle delta. So this delta will be the phase shift between EQ prime and VB, and the gamma is the phase shift between V terminal and VB. It is not necessary to have VT as our reference, especially if you connect this to infinite bus through the transmission line. Assume this is your reference and this is VT. So in this case, this angle would be gamma, as we put it here. So this is the current. Assume this is the current, and this is the phi. What is phi? What is this angle?
Phasor angle.
Phase angle.
Phase angle. And delta?
Power angle.
Power angle. So this is the current, assume this is the current. So can we start from terminal voltage and the current and we build this phasor diagram? If you can add to VT, if you can add the voltage drop here over this reactance, then you can get E prime. So you multiply voltage drop here is I times JXD, and in this case, this will be perpendicular to the current. So this is 90 degrees. So IXD prime perpendicular to the current, and summation of VT plus the voltage drop gives you the voltage E, the internal voltage, induced voltage inside the machine, or internal voltage E with angle delta with respect to the reference. Okay, so this is the phasor diagram, and definitely this is the the definition of all this. Now let us take this machine and connect it to the infinite bus and see what the condition for stability in this case. Okay, this is the case A, single machine infinite bus. You have here the voltage source, and this is the transient reactance, and you have here transmission line impedance, and this is the terminal voltage, V terminal somewhere here. And assume that there is no load here, but the current will be the same up to the infinite bus. So this is infinite bus. What is the characteristic of infinite bus? What do you mean by infinite bus? If you can anybody remind us what is the characteristic of the infinite bus? Hussein, Ali?
The voltage is constant, magnitude and phase.
Okay. What else? We need more interaction. We need يعني Ramadan Ali?
Yes, doctor. The power is
I didn't hear you, Ramadan.
yes, the power is large.
I heard the power is, and then after some time large. What is missing? طيب أيوب الخليفة.
The frequency as well will be constant.
Frequency will be constant. Okay. What else? Any answer? Infinite bus can be represented by ideal voltage source. There is no internal impedance. This is why the voltage is constant. Whatever the current, the voltage here is constant. Whatever the current drawn from the infinite bus الانفينيت باس represent يعني الانفينيت باس is equivalent to the rest of the system. يعني this is one machine and the rest of the system, which is very huge compared to a single machine, definitely, is represented here as infinite bus. The infinite bus is the ideal voltage source, so there is no internal impedance, and the voltage here is constant. The frequency is constant. Why the frequency is constant? And actually, the frequency is constant is a result from infinite bus has infinite inertia. Yeah, assuming the other generators in the system are combined together in one machine. So this machine will be very huge compared to this single machine connected to the system. So H will be infinity. And the machine is very heavy. So the H will equal to infinity. And if H equal to infinity, if you go back to the swing equation, when we say 2H, or let us say d square delta by dt square equal to omega s b mechanical minus p electrical over 2H. So this is the swing equation. If you have here H equal to infinity, infinite bus, H equal to infinity. So in this case, you have the acceleration equal to 0. So the speed is constant. So the frequency is constant. So infinite bus means infinite inertia. Infinite inertia. And also infinite short circuit capacity.
Doctor, what do you say now?
Sorry?
What you said last? I didn't get it.
Short circuit capacity.
Okay.
You mean short circuit?
Okay, short circuit capacity.
Short circuit capacity. Short circuit capacity equal to V times I fault. Short circuit. I short circuit. If you have here constant or ideal source here, V is constant. How, if you do short circuit here, how much is the current? How much is the current here? If you do short circuit?
Infinity.
Infinity. Infinity. I short circuit equal to infinity. وبالتالي short circuit capacity equal to infinity. Infinity short circuit capacity means that the system is very strong. It's very strong at this point. Whatever you connect the load, you remove a load, you do whatever disturbance, the voltage is constant and it doesn't or hasn't been affected by any disturbance. So this short circuit capacity is usually used in real life when you want to connect, if this is a utility, and you want to connect an industrial plant here to this bus of Saudi Electricity Company. So you have to know what is the short circuit capacity here. You have to know the strength of the system at this point. طبعا of course in order to do your fault analysis and protection, sizing, circuit breaker sizing, and so on. So you have to know the short circuit capacity. Usually, if you are given the short circuit capacity at a certain bus, short circuit capacity can be approximated to 1 over X equivalent or X equivalent at this. طبعا الشورت circuit current equal to V over X, and V square voltage is approximately 1 per unit. Current here will be 1 over X approximately. So short circuit capacity can be represented by 1 over X equivalent. So if you have the utility and you know the short circuit capacity of this, so you can do your analysis of your plant. So this is my plant now, and here I can reduce all the network here by its Thevenin equivalent. V here equal to 1 per unit, and this is X Thevenin. X Thevenin equal to 1 over the short circuit capacity. So if you have a short circuit capacity again equal to infinity, that means you know there is no Thevenin impedance and the voltage here is constant. Whatever changing of the load here will not affect the voltage. Okay, so assume that we have here a voltage source, which is the one machine connected to an infinite bus. The infinite bus has maybe you can assume it as your reference, or you can have your reference as something else. Maybe terminal voltage can be considered as a terminal the reference. In this case, the V bus has an angle or phase shift between theta prime and this, and so on. So assume that the V bus equal to this. So in this case, the total reactance between this voltage source here and this one is summation of XT prime plus XL. And if you have a transformer here, also you take it into consideration. So you these reactances are connected in series. And in this case, can you get the power transferred from this point to that point? How much the power transferred here between this point and this point? Can we get it?
Yes.
Power transfer
Yes.
between any 2 points.
Yes.
Yes, we can.
Equal to what?
E dash
V1 V voltage at this bus multiplied
E
by
prime?
the yes
E
E
prime?
prime yes multiplied by V
Okay.
divided by the some of the reactances
Okay.
multiplied by the sign of angle difference between the delta and theta prime.
Okay, great. So this is the BE equal to E prime V over X, and this is X summation sine theta, and the theta here is delta minus theta prime. So delta minus theta prime, which is sine, which is theta there. So for infinite bus, it's equal to infinity, and the derivative of theta prime equal to 0. Sorry, equal to omega s, constant speed. So you have a constant speed here, as we proved here with this swing equation. If you know, if h equal to infinity, in this case the speed is constant. So this is the synchronous speed. Omega s is the synchronous speed. Abdulaziz Khalid, do you have a question? Abdulaziz.
yes دكتور.
Yeah, please.
If we are modeling the infinite bus as an ideal constant or voltage source, then what does draw the current from the generator or the machine?
But you have here load here, and you have here load, and you connect here a load. Okay, so this is the infinite bus, and whatever the current drawn here from the infinite bus, it will not affect the voltage. Okay, and assume that this is the voltage source, and if you have a reactance here, if it is not ideal, and this is your load. Okay, so the voltage here is V, and assume that the voltage here is E. So if you have here X Thevenin, in this case, if you increase the load here, this is the load. If you increase the load, what will happen for the voltage? What will happen for the voltage?
It will drop.
It will drop.
Will start decreasing. And we have more voltage drop on this reactance. But if this is an infinite bus, the reactance is zero. Why the reactance is zero? Then infinite bus means in the short circuit capacity equal to infinity. The voltage here is constant. It doesn't change. So you have here zero reactance, and the voltage at the load, if you increase the load, if you decrease the load, you have a constant voltage here. Is it clear, Abdulaziz?
Yes, thank you, Doctor.
Okay. Any other question?
But doctor, if the load is continuously increased, if we have a continuous increase in load and continuously, will it not eventually affect the infinite bus?
In terms of voltage, you will not affect.
Okay.
طبعا هو الانفينite bus يعني to be frank with you, الانفينite bus is some kind of approximation.
Okay.
يعني it is not in the real life.
Not ideal. Okay.
It is not يعني in real life you can have a voltage equal to a constant, a frequency equal to constant, whatever. But you know, this is just an approximation. يعني when we say the current here is infinity, يعني this is not يعني practical. You have very high current, yes. You have very high short circuit capacity, but يعني infinity is some kind of يعني extreme, just to explain يعني. Okay. إنما
Yes.
طبعا in real life definitely the voltage will be affected.
Thank you, doctor.
Okay. This is Ayub.
Yes, doctor. Doctor, we have said that, the short circuit capacity represents the strength of the system. So
Yes.
is it function of the voltage? So higher voltage, so the system strength will be stronger, or it's not related with the voltage?
It is not, related to the voltage level. يعني الvoltage يعني sometimes we calculate this short circuit capacity in terms of per unit. يعني in terms of per unit, this short circuit capacity equal to approximately the voltage would be 1 per unit. ال 1 per unit دي could be 380 kilovolt, could be 132 kilovolt or 115. Okay, so the base value of the voltage is different from one section to another if you have a transformer. Right, Ayub?
Yes, doctor, right.
So this voltage could be 1 per unit could be 380 kilovolt or could be 69 kilovolt. So if you calculate the short circuit capacity in terms of megavolt ampere, yes, it will be affected voltage 380 kilovolt or something like this. However, usually we can have it in per unit. So in this case, the voltage will be 1 per unit, and the short circuit will be in per unit, and this X Thevenin also will be in per unit. So definitely, yes, the voltage, if you take it by the actual values, the short circuit capacity and transmission level will be definitely higher than the short circuit capacity of distribution level. Okay.
Thank you, Doctor.
So the speed here is constant, and if the H infinity, H equal to infinity, if you substitute in this equation, H equal to infinity, well, the acceleration equal to 0. So theta double prime dot, theta prime double dot equal to 0, and then in this case, theta double dot equal to delta double dot. Okay. So assume that there is no damping, there is no friction, there is no eddy current losses, nothing, the system is lossless. In this case, we can write the swing equation as such. Theta double prime, which is delta double prime also, equal to synchronous speed 377 radian per second over 2h, which is the inertia constant, equal to times B mechanical minus B electrical, and B electrical is calculated as such. E prime times V over X reactance in between E prime and V, and this theta is the phase shift between E prime and V. So this is the swing equation, and BE versus theta can be plotted, as you know, by this sinusoidal shape here. So this is BE, and this is theta. BE and theta. BE equal to E prime V, so it can be right BE equal to BE max sine theta, and this BE max equal to E prime V over E prime times V pi over X. So this is the BE max. This is the maximum electrical power, and this happen at theta equal to 90 degrees. Okay, where is the operating point? The operating point, this is BE. This is how BE changes with theta. If you are given a certain power delivered at steady state, assume that at steady state, the power here equal to 0.5 per unit. So we can say at steady state, B mechanical equal to B electrical. Assume that the system is lossless. وبالتالي فالبي mechanical equal to 0.5. And as we mentioned last class, and we will keep B mechanical constant. It doesn't change. What will change due to disturbance is BE. BE will change due to the disturbance. So at steady state, B mechanical equal to B electrical. If this is the B electrical at steady state, in this case, B mechanical equal to 0.5 and will be kept constant. So to identify the operating point over this sinusoidal waveform, you have to draw the mechanical power. So this is the mechanical power and it will be constant over the angle here. So B mechanical equal to 0.5 and constant. The intersection between B mechanical and B electrical gives you the equilibrium point. As you can see here, we have two equilibrium points. A is an equilibrium point, B mechanical equal to B electrical, and also B is an equilibrium point where B mechanical equal to B electrical. So what do you think? Which one is the proper one?
Both.
Max.
A or B?
Oh.
Both A and B, because
the machine can operate here.
A will A.
And the machine also can operate here. But which one is the proper one or appropriate
A
one?
is the proper.
Or we can say stable one. Which one? رمضان علي. خلينا ناخد hand by hand كده. رمضان علي.
Yes, doctor. A is stable.
A is stable. تمام. أيوب.
A, doctor, is stable because B, you know, if B will pass it through after 90s means it's, you know, he passed the instability.
تمام. يعني you want to say no 90 is the stability limit for the angle.
Exactly, yes.
That's what you want to say. Okay, you are right. A is a stable equilibrium point. Equilibrium point. B is unstable equilibrium point. Why we call it A is a stable equilibrium point and B is unstable equilibrium point?